Hi, welcome to a brief introduction to astrophysics. My name is Hanish, and today I'm going to take you on a quick journey through the universe, just enough to build a map in your head and spark curiosity for what comes next. By the end of this video, you'll be able to look at the sky a little differently, less like a mystery and more like something you can actually understand. Let's begin by answering a simple question. What is astrophysics? Astrophysics is a branch of physics that studies celestial objects and the universe, stars, planetary systems, galaxies, and more. And the fun part is, we do this using signals that reach us across space. Most of the time, that signal is light. Anything from radio waves to X-rays and gamma rays. But we also learn from other messengers, like neutrinos and gravitational waves. So briefly, astrophysics is physics applied to the universe. So, why do we even need astrophysics? Because everyday physics, like the stuff we use for cars and baseballs, is amazing, but it's not the whole story. Newton's laws work incredibly well for most daily life, but the universe pushes us into extremes. Huge masses, high speeds, strong gravity, and even quantum effects. Astrophysics is where we take those physical ideas and test them on the biggest stage there is. Here's a picture of a giant cluster of about 3,000 stars called Westerlund 2, located about 20,000 light years away. Those tiny shiny dots you see are stars, real suns, some of them possibly much larger than Earth and even larger than our sun. And here's the wild part. When you look at this image, you're not seeing it as it is right now. You're seeing light that has been traveling for about 20,000 years before it finally reached Earth. Even light, the fastest thing we know, moving at about 300,000 kilometers per second, takes time. Space is that big. A natural first question that hits us when we think about all of this is, where did it all begin? According to the Big Bang model, the universe has a history of about 14 billion years. But that immediately raises questions that make astrophysics exciting. How did the early universe evolve into galaxies, stars, planets, and eventually us? And how do we even know any of this when we can't go back in time? To answer these questions, we're going to start by finding a location in the universe. You may or may not have heard the term galaxy. A galaxy is a massive collection of stars, gas, dust, and dark matter, all bound together by gravity. And many galaxies contain star systems and planetary systems with planets orbiting stars. Based on what we observe, galaxies come in a few common shapes: elliptical, shaped like an ellipse, spiral, and irregular, no single clear shape. Our galaxy is the Milky Way. It is a spiral galaxy with multiple arms extending outward from its center. And the Sun, our star, is sitting in one of those arms, not at the center. But even saying our galaxy is still a huge scale. So let's zoom in. When we zoom in, we start seeing what galaxies are really made of: stars, billions of them. Some are closer, some are much farther, and just from an image, it's natural to ask, how can we tell which stars are near and which are far? Or, which star is hotter than its neighbor? Those are not just philosophical questions. We can actually answer them using physics and light. We'll come back to this when we talk about the cosmic distance ladder in another video. Now let's zoom in even further, down to something we can call home. Here we are, our solar system, with the Sun, Earth, and the other planets. And notice the path it took to get here. From universe to the galaxies, then to the Milky Way, and then to our solar system. That zoom in alone should tell you something about scale. If one galaxy contains hundreds of billions of stars, how many other systems might exist out there? Let's transition to a very familiar object we can observe, the Sun, which is a star. For a long time, many people believed in a geocentric model. Earth had the center and everything moving around it. As astronomy developed and observations improved, the heliocentric model replaced it. The Sun at the center of the solar system, with planets orbiting around it. So, what makes a star so special? A star is a massive, self-gravitating sphere of hot plasma, mostly hydrogen and helium, that's hot and bright. Think of stars as objects that can range from Earth-sized white dwarfs all the way up to supergiants larger than Earth's orbit. That range comes from different kinds of stars and different life stages. And it also tells you something important. Stars can have extremely strong gravity. Now, what qualifies as a star? Here are 3 core ideas. Stars are held together by their own gravity. Stars are supported by internal pressure pushing outward. And stars shine because nuclear fusion in their cores releases energy that eventually escapes as light. That balance, gravity pulling in, pressure pushing out, is what lets a star stay stable for a very long time. We've been talking about how large celestial bodies can be, so let's make it visual. Here's a side-by-side comparison of the sizes of planets and stars in increasing order of magnitude. When you see this, it becomes obvious why words like big and far stop being useful unless we define scales. One simple scale we use locally is the astronomical unit, or AU. Fact: the distance between Earth and the Sun is about 1 AU. Numerically, one astronomical unit is about 1.496 into 10 to the power of 11 meters, which is about 1.5 times 10 to the power of 8 kilometers. So, how did we calculate that? And can we calculate distances to other stars and planets in the universe? We also talked about stars. What about planets? How do planets differ from stars? And the big one, is Earth the only habitable planet in the universe? By now, you should have a clearer sense of the vastness of the universe, the scales at which these large celestial bodies exist, our place in the universe, and what stars are at a basic level. More to come in the upcoming videos. Stay tuned.